All right, welcome to example 3 in 8.2 in Math 20-1. This is where we solve another quadratic, well actually this is linear quadratic system. And it's worded really kind of strangely. It's talking about the height of the crate during free fall and then the height of the crate with the parachute open. And the concept here is that when the parachute on the crate opens, that's the end of the free fall, but it's the beginning of the parachute section of the fall. So that does end up being an intersection. I'm not going to get too much into the physics, but basically it's the idea that during free fall, you're accelerating, and then when the parachute is open, eventually you start falling at a constant rate. So what we're really doing in this question, and it's definitely, those classic word problems make it seem like we're doing much more than we actually are. We are trying to solve this systems of equations. Now, before we go anywhere, as soon as we start to talk about real world applications, it's important to think about how the variables are restricted. H is the height. And we know that that needs to be greater than or equal to 0. Now you can have a height of 0, you're on the ground, but we're not going to talk about, falling past sea level or something weird like that. And similarly, that time as well must be greater than or equal to 0. This is the really useful one. That's something that's going to happen again and again in math class. It's important to remember that we don't deal with negative times unless you're really explicitly told to in some kind of a weird situation. So in order to solve this, and we are going to use the quadratic formula in a few things because it asks us to go to the nearest hundredth. So we're going to be able to actually use kind of some of those tools that we have. To solve this, they're already set up for substitution because it tells us what h is equal to in both formula. So what I'm going to do is I'm going to make the right-hand sides of those equations equal to each other. And really what I'm doing here is I'm just replacing h with this bracketed expression. Now, once we get to this point, it is quadratic. It doesn't truly matter whether your a value is positive or negative, but I like it to be positive. So I'm going to add 4.9 t squared on both sides. And I'm going to subtract 750 from both sides. Now, keep in mind, like terms are important. What we end up getting is 0 on the left-hand side. 4.9 t squared is the only term that has a squared variable. Negative 5t is the only term that has a variable to the power of 1. And then 650 minus 750 is, oops, that should be 700. Where did I make that mistake? Right here. Sorry about that. So that'll modify a few things. So this is 700. And that's why we get negative 50 right here. Okay, once we're at this point, we are going to use the quadratic formula. That allows us to solve for t without worrying too much. There's a calculator technique, but this is an algebraic question. So I'm just going to put over here that t is equal to, we're going to have negative b is negative 5 in this case, plus or minus the square root of b squared, so that's negative 5 squared, minus 4 times a, which is 4.9, times c, which is negative 50. Very important that the signs are carried with them as we do this. And then on the bottom, it's 2 times a, so 2 times 4.9. Take a look back at chapter 4. If you're struggling with the quadratic formula, you have to get comfortable with it. When we do a little bit of cleanup here, we get that t is equal to 5 plus or minus the square root. That discriminant ends up being 1005, and then all divided by 9.8. Now what this does is it really branches into two solutions. When we add the square root of 1005, we end up with 3.75 seconds, rounded to the nearest hundredth. And when I subtract the square root of 1005, what I end up with is negative 2.72 seconds. And that's immediately a little bit of a trouble. As impressive as it is, you can't really, fall back in time. So this is not a solution. And it's a big reason why I like writing the restrictions on the variables, because then you catch those, extraneous answers that aren't actually a solution to this question. Okay, so the problem is that because this is a system, we've only really found how long it takes for the parachute to open. The other part of the solution would be the height, and you can use either formulas, but I'm going to use the easier one, which is that h is equal to negative 5t plus 650. So the height at which this parachute opens is negative 5 times 3.75 plus 650, and I end up with that height of 631 meters. Now, the last part of this wants us to verify our solution. I should put it into both equations, but I am going to check that if I look at the other equation, which is h equals negative 4.9 t squared plus 700, then I am checking if 631 is equal to negative 4.9 times 3.7, and I am going to use the unrounded number there from my calculator, squared plus 700. And what I end up with, and this is really important, that it's not actually 631. we got 631.274, and there's an unrounded number there as well. I should have written it in. I'm just going to write it beside now, 631.274. When we use the unrounded numbers, it works perfectly. If you were to use 631 and 3.75, you should not expect it to be perfectly equal to each other because you rounded, which is why using unrounded numbers is so important. And we get 631.274 is equal to 631.274. If they don't ask you to verify, I would recommend that you use your calculator just to double check that you got the solution correct. Okay, moving on to example 4.